Welcome to problem solving session for computational commutative algebra. I am Siddhi Balu from IIT Gandhinagar, and today we will discuss problems related to the syllabus from the course computational commutative algebra. So let us start with the first problem. So it is this, that let R is equal to K x1 to xn be a standard graded ring. So standard graded ring means degree of each xi is 1, and let m be, just a second. Yeah, let m be a finitely generated graded module over R. And suppose f1 to fr belongs to R is a regular sequence of homogeneous elements with degree fi is equal to, suppose, delta I, then we have to prove this, that h of this module, m quotiented by f1, f2, fr, this Hilbert series, is actually product I from 1 to r, 1 minus t power delta I, h m r t. So this is general result than what we have been using. So if you remember, we have used this fact that if R is kx1 to xn and R is anyway finitely generated module over itself, then for a regular sequence, f1 to fr in R, we have used this so far, that hr quotiented by ideal generated by these f1 to fr r, t is nothing but this product 1 minus t power delta I divided by, okay, again this f1 to f1 r, let me just copy this, of homogeneous elements f1 to fr in R with degree fi is equal to delta I, then this we have seen, if you remember, we have seen this where this n is again number of variables, as I said, and this happened because this is what, this is product of 1 minus I from 1 to r, 1 to r, 1 minus t power delta I into, this is HRRT. We saw this yesterday, right? This is, let me write even this, 1 by 1 minus t power n. And this is nothing but Hilbert series of R over itself. This is HRRT. Okay, so what we are given here is more general. So this was R as a finitely generated module over itself. But this statement here, that M is a finitely generated graded module over R. So this is even a general statement which we will try to prove. Okay, so any doubts so far? So this we have used in yesterday's lecture, I mean week 12 lecture, and also in, I guess, week 10 lecture. So let us start to prove this. So I hope the statement is clear. Was exactly they are saying that if we have information about Hilbert series of given module, then this quotient for any f1 to fr of a regular sequence in that in R, we can always easily find the Hilbert series of this module over R. Is it okay? Please let me know if the question is not clear or what we are trying to prove is not clear. So since f1 to fn is regular, I hope the definition of something being regular is clear, right? Please let me know if that's not the case. It's clear, right? So, okay. So then suppose, since f1 to fr is a regular sequence in M, then in R actually, over M, then clearly f1 is regular element, right? Or f1 is non-zero divisor of M. Is this clear? Because if something is regular means what? It I mean, all the fi's has to be, I mean, let me just write it for, so like a regular sequence means, uh, I'm writing it in shorthand. R ring, M is an R module, this ring M is R module. Then a sequence of f1 to fr in R is called M regular if first fi is non-zero divisor. Let me write it again. It's non-zero divisor on M quotiented by f1 to fi minus 1 M. Okay, and this is for all 1 less than yeah, 1 less than equal to I less than equal to R. And when we do this, the first element is regular over M, is non-zero divisor in M itself. Okay, so this f1 is non-zero divisor. And second is that the module M quotiented by f1 to frm is not zero, is non-zero or not zero. I mean, M, in short, what they mean is F is not equal to this f1 to frm. That's what they mean by this. Okay, so this is the condition. So the first element is f1 is anyway non-zero divisor on M. Okay, so this is M is a M regular sequence in R. So I have this map, right? Then multiplication by M will be injective map. So since f1 is regular in f1 is M regular This implies this map M to M multiplication by this F1 is injective map, right? Because if it's not injective, it will have non-zero kernel, and that non-zero kernel is an injective R module map. Okay. And see, this is true because if it has some kernel, I mean kernel is non-zero, then that element, then this F1 will no longer be regular element or non-zero divisor in my for M. So that's why this is injective map. So this implies we have this short exact sequence then, that 0 going to M. So this is just A going to F1A or small m, doesn't matter, whatever you want to give, or X going to F1X. Okay. So I have this, then we have this short exact sequence. Short exact sequence. 0 go, I mean this is injective map, this M multiplication by F1. And from here to here, I always have this surjective map, right? F1M. So this is normal pi projection in quotient F1. So this is short exact sequence. But I mean this short exact sequence, that is okay. So we know that if we have, we know that this is fact, and in fact the result from the notes that if for our module M dash M double dash, if 0 going to M dash going to M going to M double dash, since we want Hilbert series, we have this. If this is an exact sequence of degree preserving map, that is this each, if I give this name F and G, then this both F and G are degree preserving maps. Then we have this H M R T is H M dash T. So Hilbert series is additive. So Hilbert series of this M, oh, it's not this. So the Hilbert series of this M can be, I mean, is equal to addition of Hilbert series of these two module at the both end. Okay, so far we have this short exact sequence, but we want the short exact sequence to be also a degree preserving. Okay, but we know F1 is a homogeneous element. So, and it has degree delta I. So what we will do is, then we will convert this into this first map. So this is degree preserving map. This is not, this is just a projection. So here is not a problem. So what we have to do is, we have to make this map degree preserving, this mu F1. Okay, so but degree of any element. So for example, any degree alpha element will go to yeah, I mean degree alpha element will go to what? Degree alpha plus F1, right? Degree alpha plus F1 element. Degree alpha plus delta 1 element actually. Delta 1 is the degree of F1. So if I want to make this map what I can say, degree preserving map, I have to shift the degree for this module M here. So what I get is, then so we create or we obtain this degree preserving short exact sequence. 0. I want to shift it by degree delta. So this minus delta 1 M, again this is mu F1, again this is projection by F1 M, and 0. Now this is short exact sequence with uh, with the degree being, this is degree preserving map so far. So now this is degree preserving map. Pi was anyway degree preserving map. So this is degree preserving short exact sequence. So using this, what we get is Hilbert series of M RT is equal to Hilbert series of M minus delta RT plus Hilbert series of minus delta 1. Yeah. Hilbert series of this M quotiented by F1M RT, right? From the, let me call it this, if I call this star, or let us call me that, from the fact 1. Is this okay? But we know that what Hilbert series of this is. Yesterday we obtained this result, right? That if M is, yesterday we did this, I mean in week 12. So fact from week 12 or question 2, I guess, from week 12 problem solving session. We have that if M is finitely generated module, then if M dash is just degree shifted, I mean M dash is a new model with shifting of degree, and M is again finitely generated graded module, MA, where A is some element in Z. Then Hilbert series of this new module M dash T is T power this A. We are shifting the degree by A into H M R T. So it is Hilbert series of M into T power A. So here I have this degree delta, right? Degree, we are shifted it by degree delta minus 1. So therefore we get, therefore this HM minus delta R T is T power delta 1 HM R T. So therefore, hence we get that HM quotiented by F1MR T is this HMR minus whatever we had here. It is T minus delta 1. So HMRT minus T power delta 1 HMRT. So which is what? 1 minus T power delta 1 HMRT. And we got this. So Hilbert series for this first regular element is this multiple of this. And now what we do is, now what we have, since again F1, F2, FR is regular sequence. So now F2 is non-zero divisor or is regular element in M quotiented by F1, right? That's by the definition of regular sequence, that Fi has to be non-zero divisor on M quotiented by F1 to Fi minus 1. So I'm considering F2. So this F2 is non-zero divisor here in M quotiented by F1M. And now again I do. So again, this is non-zero divisor. Then again this map. Then the map mu F2 from M quotiented by F1M to M quotiented by F1M is again is an injective map again. Is this okay? This is again an injective map, and which will give us, and then following and degree of this map. And once I have this, then this mu F2 from this F quotiented by F1M. Now I shifted by degree minus 2, right? Sorry, minus delta 2. to make it a degree preserving map. So which will give me, this is degree preserving injective map. Giving us, now it will give us this exact sequence. We get this, the exact sequence, degree preserving. Degree preserving is important, okay? We are calculating Hilbert series. So everything needs to be in homogeneous setup. And again, we get this exact sequence. M quotiented by F1M minus delta 2 going to M quotiented by, yes, F1M. And now this is M quotiented by F1M. Quotiented by what? This is F2. So it becomes F2M quotiented by F1M. But this is F2M is actually F1, F2M. Note that this, when we do M quotiented by, this is just multiplication by F2. So it is F2M quotiented by F1M. But this need not be true because this need not make sense. Okay, so this when we write, it is actually F1 comma F2M quotiented by F1M, because whatever module we write here must contain this F1 as well. Okay, so it is actually F1 comma F2M quotiented by F1M, and this is this M quotiented by F1M minus delta 2. This is mu F2 M quotiented by F1M, and this is going to M quotiented by F1 comma F2M. These two are isomorphic, so this is going to 0. This is my projection. So again, now I'm applying this. Again, I'm applying this now to my sorry. Now again, I'm applying that formula for a short exact sequence of Hilbert series here, and I get that H M quotiented by F1M R T is equal to H M quotiented by F1M minus delta 2 RT plus H of M quotiented by F1 F2 M RT. And again I do the same calculation. This is again, we know that it is T minus delta 1 minus T power delta 2 into Hilbert series of this one. So again, by simple calculation, we get this, that this is H quotiented by F1 to F1 F2 M R T will be this HM quotiented by F1 M R T minus this is T power delta 2. We know this. And again, this becomes HM quotiented by F1 M R T, and this gives me 1 minus T power delta 2 HM quotiented by F1 RT. But what is this? This is what? This is HM quotiented by, let me just write this. 1 minus T power delta 2. Yeah, this is T power delta. Yeah, T power delta 2 into 1 minus T power delta 1 HM RT. Is this okay? I'm just substituting whatever we had the expression for this one. Okay, and then just repeat the argument. Okay, or what you can do is you can do the induction. Assume the statement holds for n minus 1 regular sequence, homogeneous regular sequence of size n minus 1. Then again for Fn, if I have regular sequence of size n, then I will get again this. Then for regular sequence of size n, again this F, we have the following degree preserving short exact sequence. I mean, it's just the similar argument. This 0 going to m quotiented by, now it is f1 to fr minus 1m minus delta n going to m quotiented by f1 to fr minus 1m going to, again the similar argument which we did, m quotiented by f1 to fr minus 1 quotiented by f1 to fr minus 1 comma fn quotiented by fr minus 1 and so on. So this will ultimately give me m quotiented by f1 to fr m, and this is going to 0. So this is the exact sequence which I have. Okay, and again applying that Hilbert series, we get, I mean, you can check this. This is hm quotiented by f1 to frm rt is equal to 1 minus, again here, t power delta n into hmr, not r, I'm using n, I guess. It doesn't matter. Or let me assume this for r minus 1 and r, and keep this r here. Delta r hm quotiented by f1 to fr minus 1m t, and but since I have already assumed it for t minus 1, this is 1 minus t power delta r, this is 1 minus t power delta r minus 1, so on 1 minus t power delta 1 hmrt. Okay, this is what we will get, and that's exactly what is product I from 1 to r hmrt, sorry 1 minus t power delta I hmrt. Is this okay? The only thing which we had to do was obtain the exact sequence here, which we have seen. This degree preserving exact sequence is actually playing the role, and also the fact that we already yesterday proved this, that where is, yeah, we also proved this result yesterday, that how when we shift the degree, how its Hilbert series look like with respect to the original module. Okay, so using these two facts and obtaining this uh, exact degree preserving exact sequence, we actually get this. Is there any doubt here? Any doubt what is done and anything? Oh, no doubt. Okay. So now, so this was the result which we proved multiple times, and it is very useful to calculate the Hilbert series. At least in case of polynomial ring, we know how this also look like. In case of, I mean, how HRRT is 1 minus t power n. We know this. Okay. So in that case, it is easy to calculate. I mean, this result is easier to obtain the Hilbert series. Okay, so let us move to this next question. So let R is equal to K, X, Y, Z, and graded and graded with G length. Okay, so it is graded lexicographic order. Let I is equal to this y square minus xz, x square minus yz, and this z square minus xy. This is my ideal, and J is equal to initial ideal of I, again with respect to G leg of I. Let us denote this by G leg order by this. Okay, so this is just doesn't matter. Yes. Initial ideal with respect to graded lexicographic order. Okay, then the question is, then we have to choose the following. Choose the correct. First one is that Betti number, this graded Betti number 0, 1 of I is 0, and Betti number of 0, 1 J is greater than 0. Second one is this beta 0, 1 I is 2, and beta 0, 1 of J is 2. Third one is this beta 0, 2 of I is 3, and beta 0, 3 J is 1. Beta 0, 4 of J is 1. Okay, we are doing this again because yesterday we couldn't actually properly go through the Betti number question. So let us do this again today. And this also includes the initial ideal. So we will also try to recall what was Gröbner basis, what is initial ideal, and how to and what is Bookberger criteria, and so on. Okay, so first we have to find this initial ideal of J. Okay, we have to find this, and I is given like this. So let me write I again. So let me just copy this instead of writing. I is given here. Oh, I is this. So let me arrange the I in terms of what I can say, the initial term. So G like, if you remember, it is x1 greater than x2 greater than xn, and if for x power a1, xn power an is greater than x, or yeah, x1 power bn, sorry, b1, x power 1 bn, if first summation ai greater than summation bi, this is first, and second is if summation ai is equal to summation bi, and this ai ai minus bi is greater than 0 for the least I such that ai not equal to bi. Okay, so x square is always greater than y square. Oh, sorry, x square is always greater than, yeah, I mean, in our case it is xyz, so x square is always greater than y square in our case. Okay, and so this is everything, I mean, it's homogeneous. So if I is again my this ideal, so I'm just rewriting I with the initial term first. Okay, so initial term here is minus xz y square, x square minus y square, comma, minus xy minus plus z square. Is this clear? Because x is greater than, I mean, these two have same degree. This is homogeneous ideal. Okay, I is a homogeneous ideal first of all, with all the elements generated by degree 2 term, degree 2 polynomial. And here this 1, 0, 1 is minus, if I take this 0, 2, 0, 1 minus 1 is 0. Here AI, this is my A1, this is A2, sorry, B1, non-zero with A1 minus B1 greater than 0, right? 1 minus 0 is greater than 0. So that's why this first term, this xz is greater than y square. Okay, so initial, so if I call them f0, f1, f2, then initial term of f1, f0 is minus xz, initial term of f1, f1 is x square, and initial term of f2 is this xz, sorry, xy. Is this okay? Any doubts here? I mean, we can get rid of this coefficient, doesn't matter, but that won't affect the calculation in general. So we have to find the initial ideal of this J. So what we have to do is, so what is initial ideal? It is generated by initial terms of all the elements belong to this ideal I. Okay, and in general, initial ideal of I is not equal to initial ideal of I, initial terms of F, such that, I mean, if in general, if I is generated by F1 to Fr, then initial ideal of I need not be equal to initial terms of this F1 to Fr. Okay? And that exactly, for exactly this reason, we have something called as Gröbner basis. So in case of Gröbner basis, this condition is satisfied, that if I is generated by a Gröbner basis, then its initial ideal of I will be generated by the initial terms of that Gröbner basis. Okay, so how to find that Gröbner basis? So what we do is we find S polynomial or S pair of some, what I can say, S pair of polynomials. So what is S pair of f0 comma f1? I mean, we have used this S pair already in previous lectures, and this is in f0, f0 minus LCM, in f0, in f1 divided by in f1. This is all with respect to this graded lexicographic order, okay? And this is f polynomial in general. So instead of f1, f0 comma f1, I can just substitute f comma g, and this is s polynomial. And what we do is we find this s polynomial, and in order to check whether these given generators form Gröbner basis or not, what we do is we calculate this s polynomial. Whatever we get, we check its initial term, the leading term. If the leading term of this ideal, of this S polynomial, if that leading term belong to the leading term generated by my initial generators, for example, in this case, if ideal generated, if whatever leading term I get for this S polynomial, if that leading term belong to this ideal in F1, in F2, in F3, sorry, in F0, F2, F0, F1, F2, that is ideal generated by minus xz, minus x square, minus xy, then we can say that for each such S pair, if that happens, then we can say that this F1, F2, F3 or F0, F1, F2 forms a Gröbner basis. Otherwise, if we find any S pair for which this initial term is not in this ideal generated by initial terms of f0, f1, f2, then we add that polynomial or that S pair in our generating set to obtain the Gröbner basis eventually. Okay, and so we will do that. We will calculate these S polynomials and we will try to obtain this initial initial ideal j of I. So this is LCM of initial term of f0x minus xz comma x square by minus xz f0 minus LCM of. So in this case, since there are three polynomials, we will have to calculate these three S pairs. For f0 f S pair of or S polynomial of f0 f1, f0 f2, or f1 f2 and f1 f2. Okay, so this is f0 is again minus x square xz x square divided by x square and f1. And LCM of this is what? Minus, if I take minus as well, it will be, we can either take minus or we can get rid of the minus. That won't affect the S polynomial in general. Whatever we will get, either polynomial P or it's minus or minus of P. Okay. So if I keep this minus, so I get x square z by minus xz f0 minus, let me write this f0 as well. What is f0? It is minus xz plus y square minus, again here it is same, minus x square z by x square. F1 is x square minus yz. And when I calculate everything, it is x into minus xz plus y square. These calculations are a bit lengthy, but we have to do this. Which is minus x square z. Oh, this becomes plus. This minus x square z plus xy square plus x square z minus y z square. So this becomes S of f0 comma f1. So this gets cancelled, these two terms. I get xy square minus yz square. And here initial term, so initial term of this S f0 comma f1 is xy square, right? This is degree 3 polynomial, homogeneous degree 3 polynomial. So the leading term is xy square. Okay, again, we are applying graded lexicographic order. So this xyz, and whether this belong to this ideal generated by initial term of this ideal. It belongs, right? It belongs to this ideal because I can multiply it by minus y and I get this. So this belong to my ideal generated by initial terms of f0, f1, f2. So we don't need to add this to my Gröbner basis or the Gröbner basis which I'm trying to obtain. Now again, I have to find this f0 comma f1 and f0 comma f1 we just calculated, and it is again LCM of, let me just copy this. Just here we need to f2. Okay, and again the calculation LCM of f0 was minus xz, f2 was minus xy, right? Yes, minus xy, here it is minus xz f0 and minus LCM of again minus xz minus xy divided by minus xy f2, which is minus xyz by minus xz f0 minus, or just get rid of this minus, and f0 was again minus xz plus y square minus LCM of, this is again xyz by minus xy, f2 was minus xy plus z square. So this get y into minus x z plus y square minus z into minus xy plus z square. So this is y cube minus or plus. Yeah, minus. Here it's minus, here it's plus. So I get minus y cube plus z square. Sorry, z cube. This xyz gets cancelled here. So now whether this, so leading term again, initial term of this s f0 comma f2, whether this belong, which is minus y cube, right? This is again homogeneous polynomial with, we have the degree x greater than y greater than z. So y cube is greater than z cube. So leading term of this polynomial is this s pair is this, and we can see that, oops, sorry, it doesn't belong to this ideal. This ideal generated by initial terms of xz, x square, and minus xy. Okay, so we have to add this s pair. I mean, we can add this or minus of this, doesn't matter. So therefore, I have to have this f0, f1, f2, and I take this f3 as y cube minus z cube. Now again, I have to, so far I have this extra term in my Gröbner basis compared to what I had as a generator of my ideal I. And now the final one, I want to calculate this and check whether again this, the initial of this S pair belong to my ideal or not. So it is again just, so it is f1 comma f2. So f1, here I need to have f1, this is f1, and that's it. So we have to calculate this. Now LCM of the LCM, the leading term of f1 was x square minus xy by x square into f1 plus LCM of, again, x square, this is x square minus comma minus xy by minus xy. I hope that's correct. Yes, into f2. And now I have to check whether, what is LCM of this? It is x square y divided by x square f1, and f1 is my, let me write here f1. Again here it is x square y or minus x square y, doesn't matter, minus xy f2, which is minus y into f1, that is x square, sorry, x, f1 is, yeah, f1 is x square minus yz plus this is x into, this minus gets cancelled. Oh, this is supposed to be minus here. Minus x into minus xy plus z square, which is minus x square y plus y square z plus x square y minus x z square. So which is minus x square y get cancelled. This is y square z x minus x z square plus y square z. And this again belongs to my new ideal. This ideal x z x square y. And so leading term again, or initial term of this s f1 comma f2, which is minus xz square. This belong to my ideal. This. And now I have already added my fourth member. So this belong to this ideal generated by y cube. I mean, we have to add this fourth element to check. Okay, so every time when we do the calculation for Gröbner basis, and we check whether the initial term of the the whatever S pair we have calculated, whether it belong to the initial ideal generated by the existing generators of I, we have to consider this new FIs which we have added to the Gröbner basis or this generating set of I. Because if I had something like this, maybe y cube or y power 4z, something like that, then y cube divides this term. Okay. And then whatever polynomial we maybe had here, we don't need to add that polynomial in my Gröbner basis, because initial term of this element is now divided by this new element which we have already added to my generating set of I to obtain the Gröbner basis. Okay, so please let me highlight this. This y cube also needs to be added here. Okay, so that's okay. So my Gröbner basis for I, Gröbner basis of I is now this 4 polynomials. Let me just write them down. Y square minus xz, x square minus yz, z square minus xy, and y cube minus z cube. And along with this, my now j, the initial ideal become this 4 minus xz or xz, x cube, x square, xy, and y cube. This is my j. That is my initial ideal of I. Is this okay so far? So in order to find the j, I had to calculate the Gröbner basis of I. Now what we want to find, so we have now the initial term, or sorry, initial ideal of I. We have to find the Betti elements. Sorry, we have to find the Betti numbers for this. So again, we know how to calculate the Betti, sorry, how to calculate. So to obtain the Betti number, we need to have the free resolution of my module or my ideal. So we have to calculate the resolution for this ideal I. Okay. And so we know how to calculate that. And we have to find the CGGs, and the coefficients will actually give me the matrix, and that will give me the, what I can say, the, sorry, that will give me, yeah. Yes, that will give me the Gröbner, the Betti number and free resolution of this ideal I. So how to start? So this I is here. First, we have asked the question about Betti numbers of I and Betti numbers of J both. So let me just write the bit, try to calculate the, here it's I. And since I has 3 minimal generators, okay, so it will be R3. I mean, this is Gröbner basis, which we needed to calculate this initial ideal J. To calculate resolution, we don't need to include this fourth element here, okay? I mean, it's not needed. And also we are finding this minimal free resolution. So, and also all these are, so we saw this, we have to do this -2 I from 1 to 3. This we did yesterday. We had this observation that if if I is generated by F1, F2, Fk, and each has degree delta k, then this observation or fact that summation r minus delta I from 1 to k to I is equal to F1 to Fk is a degree preserving map where delta I is degree of Fi. This is observation already made in the lecture. Okay, so we have this here, and this is just each Ri going to one generator of I. So this, when I write this R minus delta I, this R minus del 1 component will go to this F1, okay? It can't be going to this Fk here. So we have to take care of degrees when we send these elements, okay? And so this we have from the observations. And now we have to calculate the CGGs of this to get my, so this is my R0, this is our R1, we want to find CGGs of this terms here. So what can we have? So let us not, so x into this term, y square minus xz plus z into this x square minus yz. Let us check the plus minus signs here. I think it will be, let us check. And plus y into this last term minus xy. Here xy square get cancelled with xy square here. Okay, this one is correct. Here x square z get cancelled with this x square z. It is correct. Here again this, so these first two terms got cancelled. This got cancelled. This x y z square get cancelled with this one, the first term here. So I get my first CGT to be x, z, y. Is this clear? X into this f0, f1, f2. We get these elements here. And now again we have to calculate the second if possible. If I multiply first one by z, then I get this z into y square minus xz plus, so now I have zy square and here I have yz. So, and here I have, so it's y x square minus yz plus x z square minus xy. So if I do this, this will again give me one CGT. See here, zy square get cancelled with this zy square and so on. So the second one is zyx. And now again, whatever you do, this can never become any R multiple, can never have. I mean, this becomes now injective. And again here, it is degree minus 2. And here we are multiplying again by degree 1 element. So to have this again degree preserving map, we have to shift it by degree 1 more in this R minus 2. So it is R minus 3, I from 1 to 2, since there are only 2 elements. Is this okay? How it is obtained? These are just CGGs. So the Betti numbers for I was asked for beta 01, beta 01, beta 02. Okay, so let us calculate what is beta 01. So beta 01 means, this is R0, by the way. This is R0, okay? I just consider this as R0 and this is my I actually. So beta 01 means degree 1 element in beta 0. So that's not there. So it's 0 actually. Just a second. Yeah. That's okay. The second one is beta 01. Beta 01 is actually 0. That is okay. Now beta 02 is asked, right? Beta 02. Beta 01, beta 02, yes. Beta 01 is 0. Beta 02. So degree 2 elements in this. We have this. There are 3 elements here. So beta 02 is 3. Is this okay? Degree 1 element, there is no degree 1 element here in R. Okay, and here we have degree 2 elements. There are 3 degree 2 elements. Okay, so this is my R or I. So therefore, the first in these options, the first one stays, but second one is wrong. Second one becomes wrong, and third one is correct so far. So first and third. So we have to check now for Betti numbers of this J. And note that here the Betti numbers are asked for this 0, 0, 0 and 0. So what this means is they are asking the Betti numbers of the zeroth component. The zeroth component is ideal itself. Is that okay? So when we asked for beta 0, 1, the Betti number, the graded Betti number 0j, for example, then it is whether j degree component is available in F0 or not. F0 means this R0 or not. So R0 is I itself always. So J0 is J itself. And they are asking whether J0 of 01, 02, 03, 04. So J0 means whether in J degree 1 elements are available or not. So it's no, right? So beta 01 of, this is I actually. Let me write here I. Beta 01 of J is 0. No degree 1 element is available in J. Beta 02, there are 3 degree 2 elements available here. So there it is 3. Beta 04, right? Beta 04 is 0 and beta 03 is 1. Okay, so that's what we are getting here. So beta 03 is 1 and beta 02 is 2. So this is the correct answer. Again, beta 04 was 0. So this is not the correct one. And this one, that beta 01 is greater than 0, that's false. Beta 01 was anyway 0. So sorry. So this is also false. So is that okay? Is this okay? Okay, it's clear, right? So let us first once again go to Macaulay 2 and check for the resolution and how the Betti numbers, again, to read the Betti numbers in Macaulay 2. Let me share the screen here. Just a second. Let me share the screen. So I have this S or R. Our ring is R. So let us call it R. Q, Q, X, Y, Z. And okay, but we also want R to have this graded monomial order to be graded lexicographic order. If you remember, this is the word for graded lexicographic, to assign a graded lexicographic order to the ring. Okay, and I is my ideal, whatever it, y square minus xz, x square minus yz, and z square minus xy. And see here, when Macaulay 2 we give order, it actually, when takes the generator, it already arranges it in the descending order of monomials. So this minus xz is actually leading term. This minus xy is also leading term. X square was anyway leading term of this polynomial. Is this okay? So, and so let us calculate this resolution of I on and give this a name C. Okay. This is the resolution of I, which we anyway calculated. And it's exactly maybe what we had minus. So it took this first one as minus xz and minus yz and so on. So that's why it is giving me minus yz. So let it be, whatever we calculated is not that different. So is there any error? The first one is x z y square, x square y z, and z square x y. Was this generated? Okay, that's okay. That's not a problem. Still, and when we do this c dot dd, it gives me all the information about all the maps. So see here, all these are degree 2 components. Okay, when this 2, 2, 2 is there, it means this R3 is just direct sum of R with shifted degree minus 2. Okay, that's what this 2, 2, 2 here means. Okay, and when I do this Betti of resolution of I or this C already, which we have, it gives me this information. And yes, when we calculate or when we read this Betti numbers here, this first row represents what we say, the F1 component, this R0 here. So this is R0, which has, so yeah, it is my R0, R1, this is R3, sorry, R2. So how my exact sequence is, just a second. How my exact sequence here is, it is this, right? This is 0 going to R1, going to R2 and R3. So this non-zero terms here, this non-zero term here, R0, this R1 and this R2 here. This is R2. These terms are actually, this represents R0, R1, sorry, R1 and R2. Okay, so when I say I want to find what is beta 0, 0, so R0, I said that we assign the R to be of degree 0 in the first coordinate. I wrote R0 there. Okay, and so if I want to calculate, I wanted information about beta 0, 2. So it means beta 0, so it is first column, and 2. So it is here, beta 0, 2. So it's not available, so it must be 0. Beta 0, 0 is 1. Okay. And now second, if I want to calculate beta 1, 2, for example, then beta 1 means I need to look at this first column. Okay. And then in this first column, when I look at the second row, it means beta 1 plus 1. So beta 1, 2. So let me just write it here. I wrote this formula yesterday. This gamma I comma j, if I have, is actually beta 1 comma, sorry, 1 comma, sorry, I comma j, I comma I plus j. Okay, where this I is my module fi and this j is degree j component, or this f number of, this is the degree j component which we want to calculate. Okay, so the table we had was this. Okay, just a second. I will have to stop sharing. If possible, can you switch the screen on your, it will be on the top side. Or let me just stop sharing this for now. Let me check. So here the columns were 0, 1, 2, and here it was 0 and 1, and 0 0 1. So this as I already said, this we consider R0, the 0 degree component. Okay, so see, R00 will always be 1, and here it's dot, and then I have here 3 and 2. So this is my gamma 00, this is my gamma 1 1, this is my gamma 1 2, this is my gamma 01, sorry, 0, gamma 10, gamma 20, gamma 01. Yeah, that's how we calculate. Sorry, we read it. Okay. So when I look at, let me give this name. When I look at this component here, this is what? My gamma 1 1, right? Which is 3, which is what? Which is beta 1 comma 1 plus 1, which is beta 1 2. So what does this imply? Number of 2 degree component in my F1. In F1, the copies of F minus 2. That's what it means. So here, this is my R1, which is my F1. What are the number of copies of this minus 2 component here? It's 3, right? There are 3 copies. So that's what this 3 means here. Okay. Similarly, now here. Now I am going to F2. So all these terms here. So 1 degree component is 0 here. This is what? Beta 1 2. 2 degree components are 0 anyway. So that's not there. And similarly, now if I go to see this, it is what? It is gamma 1 2. So it is gamma, sorry. This is gamma 2 2. Let me just correct this. Gamma 2 1. So gamma 2 1 here, it is gamma 2 2 plus, which is beta 2 2 plus 1, beta 2 3. So it is degree 3 terms in beta 2. So how many degree 3 terms are there in beta 2? 2, right? So that's what they're saying here. Is this okay? Now, this is my Betti table in Macaulay 2. So is this okay? How to read? So the easier way to read is in F1 degree 0 term, in F1 degree 2 term, in F1 degree 3 term, and so on. Now, when I look at column 2, it is F2 degree 2 term, F2 degree 3 term, F3, F2 degree 3 term, and so on. Degree 3 term, degree 3 component. So that's how we need to read in Macaulay 2. Is that okay? And let me share this screen back just to see the Betti numbers for what I can say, the J, which we needed to calculate. We also have to calculate the, let me stop this, or is it okay? We may have this. Yes, so again, so J is my, now here, J is my ideal lead term I. Okay, again, it contains this Y cube. And again, since we didn't see how the Gröbner basis of I is, we can see these 3 terms along with this 4th term, which we calculate, and it's correct. Okay, so now what I want to do is, let D be resolution of J. Okay, and now I want to find this Betti of D, that is resolution of J. It is entirely this thing. And now see this. Here the we have these four components. The R3 has R3 itself. So again, the 0, 0 component is always 1. In R1, degree 1 component, in R1, degree 2 components are 3. Okay, so what was my J? J here is xz, xy, x square, right? So it has 3 components of degree 2. So here it's 3. And R1, I mean beta 1 comma 3. Here we also have this y cube, which is only one, which has only one copy. So this R3, so here the R4 which we have, it is direct sum of R minus 2, sorry, R minus 2, yes, direct sum R minus 3. So what it means is, let me share this screen. Is this screen shared already? Okay, this screen is shared also. So this screen, I hope it's visible now. You can switch between the two screens, okay? You can check that. Here, what I was saying. Yeah, what it means is this J will be here. J will be here, 0, which is my R. J is just module. And here I have this direct sum. Since J is what? J is generated by xy, x square, xz, y cube. So I want to do this direct sum. Direct sum I from 1 to 3 R minus 2. Direct sum this R minus 3, right? For this third one. So when we switch to this Macaulay 2, in R1 we have 3 degree 2 components. In R1 we have degree 3, 1 degree 3 component. So that's what here is. So the first, let me just write that table here. It is the first, only the first row here, only the column of F1. This is column for F1. It is 0, 3, 1. With 0, 1, 2. So this is my gamma 1, 1, which is beta 1, comma 2, 2, which is degree 2 component in F1, which is 3. And here in gamma 1, 2, it is beta 1, comma 3, which is degree 3 component, which is 1. Is this understandable here? Sorry. So here gamma 1 is beta 1, 2, which is degree 3 component here. And here gamma 1, 2, it is beta 1, 3, which is degree 1 component. That was only just this y cube. Here those 3 terms. So I hope this is clear, like how to read the Betti table, or yeah, I mean the information about Betti numbers in Macaulay 2. Is this okay? Okay, so I think this much is enough about Betti numbers, and you can understand like what exactly. So again, this information about Betti numbers, which was asked here, beta 1, 0, and so on, you can check this. Only this third one is correct. That third degree component in beta 0 is 1. So that's the only thing which is correct. And I think it must be beta 1, 3. I think there was typo. Yeah, beta 1, 3. Yeah, beta 1, 3 is 1. Okay, so I hope this one is okay. If you have any doubt, please. Otherwise, I will start with the next question. So now this, if you have any doubt, please ask. Otherwise, I will move to this next question. Yeah. In C question 3, in C XYZ, I mean we did this previously also. This kind of question in I think week 3 or week 2. Ideal x plus 1, y plus 1, z. This is my ideal I. Let me just show. Let this be my ideal I. With whether this I contains the ideal j, which is this z, yz, y square plus y, xy plus x, and xy minus y or not. We have to check. So how to check this? Okay, so last time what we did was we considered each these elements and then try to give an expression whether these elements belong to my ideal or not. I mean whether each this J1, J2, J3, J4, J5, whether all these belong to my, I can write them as a linear combination of this if I call them I1, I2, I3 or not. But there is also one more thing, that note that this ideal I is this x plus 1, y plus 1, z. What is zero set of this ideal I? It is just this tuple. -1, -1, 0. Any doubt here? This much? We know that zero set of this ideal is like this. Okay. So if any ideal J contains this ideal I, so, yeah. Sorry. If ideal I contains any ideal J, this imply what? This zero set of I is contained in zero set of J, right? Contains the ideal I. Sorry. We have to check. I mean, I contains the ideal J or not. Yeah. So whether this, yeah, this zero is satisfied by every element of this J or not. That's what we have to check. So note that this Z is equal to 0 satisfied by this element here, y plus 1. So this is what? Y into y plus 1. So this actually satisfied by this element here. Similarly, this one. Similarly, this one. Again, this is x into y plus 1. So this substituting -1 here in this element. So for this polynomial z of -1, 0, -1, 0 is 0, yz -1, -1, 0 is 0, y square plus y -1, -1, 0. This is very bad notation, but let me write this. Is also 0 because substituting -y. So this becomes +1, this becomes -1, and it becomes 0. And similarly, the third one, this is x, y plus x evaluated at -1, -1, 0. This will also be 0 because -1, 1, this becomes 1 here and -1. So it is 0. Now this third element, xy minus y. So this is what? This is 1 minus -1, right? So which is 2. So it is not 0. So this last element here, so since 0 set of I must be contained in 0 set of j, means a 0 is what? 0 of some polynomial is what? I mean, all the elements of that polynomial satisfy that zero number. I mean, substituting. So if alpha belongs to 0 of I, it means f of alpha is 0 for all f belongs to I. This is the condition. But this j here, so if this -1 0 supposed to be contained in, I mean, if this was belonging to this z of j, then this -1 0 will be 0 of this ideal j. That is, this every element of this ideal j will have this -1 0 as a 0 of that polynomial. But we have this polynomial xy minus y, which is for which this -1 0 is not a 0. So that's why this, I mean, using this condition, this here, these two conditions here, we can say that therefore this j is not contained in I. Is this okay? Anyway, I was maximal ideal, so that's the case. But apart from that, is this okay? I hope. If not, please let me know. Okay. So this is also the easier way. So if I am asked to check whether, I mean, the maximal ideal of this form, if I'm asked to check whether some ideal is contained in maximal ideals of this form, then we know what the zero of this ideal is. It is just single. Then, for example, for ideal I is equal to x minus a, y minus b, z minus c. This a, b, c is the only zero of this ideal I. So if I want to check whether some ideal j is contained inside this ideal I or not, what I can do is, I have the information about the generators of that ideal j. I will substitute this ABC in those generators. If if j is some f1 to fk, if f if fi of this ABC is 0 for all fi, or for 1 less than equal to I less than equal to k, then I can conclude that this j is contained inside I. Because what we have then as z of I is contained in z of j. Using this information, I can conclude this. Is this okay? So you can, instead of, evaluating immediately in this three variable polynomial is easier compared to checking all the linear combinations, or sorry, not the linear combination, but yeah, or to check whether this every polynomial belong to my ideal I or not, and so on. It's also difficult, and since these were only binomials here, the maximum polynomial here has two terms in it. Every polynomial here has maximum two terms in it. So it was easier to manipulate, to check whether this polynomial belong to my I or not. But in general, if I have polynomial where there are 7, 8 terms, then calculating it, obtaining that linear combination in terms of the generators will be very difficult. And even if it's not difficult, it will be time consuming in that case. But having information about the zero of this ideal I and substituting it in these generators, it is comparatively easier than checking all the combinations and so on. Is that okay? If you are giving the exam, please keep this in mind. Now this fourth question. Okay, great. So Yeah. So let us do this question fourth. Again, this is true or false that let R be C x comma y. Okay. And f is a non-constant polynomial. Yeah. In R, and J is any ideal. It's any R ideal. Then the ring R mod Fj has infinitely many maximal ideals. This is what we need to check. So, how to proceed with this? Like, how can we say that f into some ideal, if I have, then it has infinitely many maximal ideals? Again, C is our uh, algebraically closed field, and we are having so maximal ideals in C are of the form x minus alpha, y minus beta, where alpha, beta, some elements from C. So we have that much information. What they have said is that this f is non-constant polynomial, but there is no such information given about J. So J is any ideal. So J could itself be uh, R itself, ideal generated by 1. No information provided about J. So without loss of generality, we can just say that, I mean, we can assume this J to be R because see, this Fj is anyway contained in ideal generated by F, right? So if some maximal ideal M contains F, it will contain this ideal Fj. So we can get rid of this J and just work with, so enough to show that F, sorry, R quotiented by this F has infinitely many maximal ideals. How to approach this? Like how to show this? Any idea? So when we say that this has infinitely many maximal ideals, it means that F belongs to, yeah, I mean this, and infinitely many such, and infinitely many such A comma B exist. Okay, then only we can say that, right? Maximal ideals in uh, what I can say. Yeah, maximal ideals in C are of this form. So how to proceed with it? So when I say this, what I mean. So we earlier, even in previous example, the zero set of this maximal ideal is A comma B. And I'm saying that this F is inside this. So what this zero set of this ideal is inside this F. So what I want to check is there are infinitely many tuples A comma B that satisfy this F. Okay, so that's what we have to check here. So just for example, consider this x square plus 1 can, I mean, in C, this belongs to this ideal x minus I y minus alpha, x plus I, y minus beta, where alpha comma beta belongs to C. I can vary this alpha and beta as much as I want, right? And then this I comma alpha or minus I comma alpha they belong to zeros, or they are zeros of this x square plus 1, right? So this is happening in this case. But here what I did was I kept my y to be free. I didn't have y in my polynomial, right? And now second, if I have polynomial of this form, then it belongs to this, right? But it also belongs to this ideal, right? Y minus alpha or something of this sort, x minus beta y. What I need in this case is either x is 0, then I am varying this y, then or what I do is I am keeping this y to be 0 and varying this x. I am doing this. So again in this, and alpha comma beta are again in C. So again there are infinitely many maximal ideals or zeros of this polynomial xy. Again, is that okay so far? So we want to generate such, what I can say, zeros or such maximal ideals such that I can show that for given this non-constant polynomial f, I can produce such a comma b such that f of a comma b is 0 for infinitely many such a comma b's in C. I mean as a tuple, a comma b in C2. Okay, so how to do it? So in general, this f in is in C x comma y, right? So how this f look like? It is summation C alpha x power, okay, Ci x power ai y power bi I from 1 to k. I don't actually uh, care about what's the degree or so on, at least for now. Okay, so it will be of this sort. So like in the first case, okay, if I have some alpha in C or some constant in C or some constant in complex numbers such that when I substitute that complex number at x, then I get 0. Then in that case, so if there exists C in complex such that, so this f is actually f of x comma y, right? Such that f of C comma y is 0. Then clearly this f of C comma alpha will be 0 for all alpha in C. So I will get in that case, this f will belong to x minus C, y minus alpha, alpha belongs to C. And we get infinitely many, therefore infinitely many maximal ideals. Is this okay? This is the first case where just by having information about x, I'm getting the entire thing to be 0. Now, if no such x exists, for example, if I take this polynomial, suppose this, okay, in this, suppose take this polynomial, x plus y plus 1. Doesn't matter whatever x you substitute, you can't actually get any, I mean, you can't get 0 here. Unlike this, here also, substituting x 0, I was getting the polynomial, I mean, it was becoming 0. Substituting 0 in this f was giving me 0. Here also substituting I or minus I in this x, I was getting 0. But here in this polynomial, substituting some value of x is not giving me 0 in any case. Okay, so, but this belongs to where? So if I substitute x to be 0, then y needs to be what? Y needs to be minus 1, right? So it has to be this. Y needs to be minus 1. So it becomes x comma y plus 1. If I choose x to be this 2 maybe. So if I choose x to be 2, then y has to be what? 3, right? I mean minus 3. So y has to be then minus 3. So it becomes plus 3. So in general, whatever k I choose here, whatever alpha I choose here, this, to make this polynomial 0, I have this, what I can say, minus alpha plus 1, which will give me 0 for this. So in general, this x minus alpha, y plus alpha plus 1 will, I mean, will contain this polynomial x plus y plus 1. So this is exactly what we will do in this case. What we will do is substitute. So for any given x, when I substitute that x in this polynomial, it's not giving me 0, right? But when I substitute some x here, some alpha, what I get is some polynomial in y, right? And this polynomial is in cy. So it has a 0. And for this polynomial, that 0 is alpha plus 1, minus alpha plus 1, right? So then what I then what's that's what I will do here. Whenever I have this alpha such that f of alpha comma y is non-zero, what I will do is I will get this polynomial in cy, and now in cy, this polynomial will have some zeros. So it will, so if my this new polynomial here, if I call this gy, if this gy has degree d, degree of g is d, then I will get at least d many, or at least one such element which will satisfy this g. And taking the union of all these elements, so for each alpha I get this, for example, m1. For alpha 2 I get m2. For alpha 3 I get m3 distinct zeros. Then taking union of all those will give me different tuples. Okay, and if I'm getting the same y again and again for different x, that doesn't matter because we are anyway changing the first coordinate here. Okay, for example, in this case, y square plus 1. If this is my f, doesn't matter whatever my x is. Okay, y has to be minus I. But that I don't care, right? Because whenever I change alpha in the first coordinate, this minus I or I will always give me the different, what I'm saying, different a comma b's, which is satisfying this polynomial f. Okay, so that's what my next, that's what our next step will be. So if no such, if no, if there does not exist, does not, if there does not exist C in C such that f of C comma y is 0, Then this f of c comma y is some polynomial pm y power m, p1 y power n, sorry, y plus 0 in cy. Okay. Then, but again in this cy, there is one more thing to notice. For example, if my f is of this form, x minus 2 y square plus x minus 2 y cube plus some maybe 7, doesn't matter. Then when I take c to be 2, this f becomes just 7, right? Which does not have any 0. But what I can do in that case is, this f x comma y, when I wrote it in this form, I can write this as some pmx y power m. I mean, what I'm doing is I'm writing this p, this f as polynomial in cx y. Okay, and now these are n polynomials. These m polynomials are here. M plus 1 polynomial are here. With each polynomial, we'll have some km zeros. I mean ki and so on zeros. So adding them finitely many times, we'll have some, what I can say. So if it has m zeros, if it has 1 0, if it has, I mean, oh, not this, this has am zeros, this has a1 0, this has a0 zeros. I will take union of all these c's. Okay, it is finitely many set. So C has uncountable many element. So like in this case, I will get rid of all those zeros of this element, zeros of these terms. And apart from that, whatever C's are left, for that each C, this for C belong to C minus union of Z of I from 0 to, and actually, we don't even need to get rid of all these. We just have to take the common 0 from this so that none of them becomes 0 at the same times. And we don't even need to take 0 of this p0. I mean, we don't want it to be a linear polynomial and so on. But still, even if we take 0 of this p0, x, it won't hurt much. So we have this. Now this f of c comma y is is a non-constant polynomial in Cy, and it has at least one root. We don't care what degree of this f is. I mean, we could care, but we don't actually need it. At least 1 0 in C. I mean, it will also might have the repeated roots, right? For example, this fcy may be something of this sort, x minus 7 power 8. Then in that case, I'm only getting 1 0. The only maximal ideal which is contributing from this C is this x minus C, comma y minus 7. Sorry. Y, right? Y minus 7. So we are not getting any much more information from this. So that's why I only care about at least that 1 0 which is available there. Say, and then say D, at least 1 0 in C, say D, then my F, this is small f, C, then my F x comma y will belong to this ideal generated by x minus c, y minus t. Okay. And note that there are infinitely many such c's. I mean, if this first condition is satisfied, then we don't care. But if this has to happen, this condition, there are still infinitely many c's for which my f of cy is non-zero, where and it is a linear polynomial at least. It is a non-constant polynomial. We can choose this ZPIs smartly such that we get this to be at least linear. And in that case, I will have at least one zero, which will contribute to my zero set. And that will give me the maximal polynomial, sorry, maximal ideal, such that it will be inside my, so, and since there are in, or I will write here DC such that infinitely many C in C minus union ZPI, we have infinitely many maximal ideals such that f x comma y belongs to x minus c, y minus dc. Okay. So hence this statement is actually true. Okay, so any given polynomial in multivariable actually belongs to infinite. I mean, this proof is, I mean, we did only this for two variables, but this can be extended to n variables. I mean, any variables greater than equal to 2. And we will get the same. I mean, in this case, we can assume the thing for n minus 1 variables, and we can again work with this y variable, which was xn variable, and we will get the same thing again. Okay, so I hope this is clear. This f is a non-constant element. It is a polynomial. Okay, don't confuse this f with this. This is ideal generated. This is not principal ideal. Okay, so when I say this is just ideal. This is principal ideal, which is contained in infinitely many, contained in infinitely many maximal ideals. Okay, and since we were asked about J anyway, this J f into J, the J doesn't anyway play a role because we already have infinitely many ideals here. So this Fj is anyway contained in those infinitely many maximal ideals. Is that okay? I mean, if we just look at this Fj, there is chance that this Fj will have even more maximal ideals such that will it have more maximal ideals or not? For example, if I take I think it will have more, or maybe, but at least we have infinitely many. That is for sure. Okay, you can think over this, whether it will have more or not, or what happens. But we at least have for a given polynomial f in multivariable ring, again in integrally closed field. Okay, this is algebraically closed, integrally closed, whatever it is. Because to have these zeros here, we use the fact that we are in C. Otherwise, this polynomial FCY need not have any zero in any, I mean, if it's not algebraically closed field. Okay, so that was one thing. And apart from this, I don't know whether we discussed this or not, but also not 9. This is, I think, question 5 that show that this was, I think, exercise given in the lecture. Is spec of kt minus t. Okay, so this we have to check. I don't actually, okay. So this k t comma t inverse, yeah. I mean, this what we did here, I hope if there is no doubt, I didn't ask, but if you have any doubt, please ask. Otherwise, I will move to this next question. Is there any doubt in this first one? I mean, this fourth, fifth question, no doubt. Okay. Okay, so we'll move to next one. This spec of, okay, so this is actually isomorphic to kt localized at this element t. Okay, this is localized with localization with respect to this multiplicative, say 1 t square and so on. Okay, so these two rings are isomorphic. Okay, and we already have seen in the lectures, we know that from the lectures that if A is a ring and F belongs to A, then spec of AF is DF is isomorphic, or this is actually homeomorphism as topological spaces under Zariski topology. Okay, and this is, oh, not this DF, this is D of F contained in spec of A. Okay, so what we are doing is, so this spec A is actually completely different than spec A. So here the elements are what? I mean, uh, as a prime ideal, they are completely different. Okay, I mean, this is a different ring than this ring here. But the associated, sorry, not associated prime, the prime ideals are in one-to-one correspondence. Okay, and this DF, if you remember, this is set of all those P in spec A such that F doesn't belong to P. This is my DF. So what they are, so this is what we saw in the lecture. So P we have from A to AF. S is my multiplicative set 1 F F square, so on. So if P belongs to spec A, I mean, I think we did such kind of thing. Even for, if you remember, we did that for, I think, in ZP. Sorry, not in ZP, in Z with respect to, I think, prime. But we did that in case of prime ideals. We were localizing it with respect to prime ideals. So the inverting elements were everything outside that prime ideal. So I think if I remember correctly, we did this and this somewhere in the lectures. But this is different than that. So it is P such that, so if I take this P in spec A and P intersection S is empty, then this S inverse P belongs to spec S inverse A. So this is the one-to-one correspondence. So here the prime ideals are this prime ideal in A. But here the prime ideals have this form S inverse PA. Okay, so as a ring they are different, but their prime ideals are in one-to-one correspondence. So therefore, this P intersection S being empty is even only if this F belongs to P, right? Because since P is a prime ideal, Okay, so anyway, P is a prime ideal, so 1 doesn't belong to P, and some power of M belongs to P, then this will imply that F belongs to P. So therefore, this is equivalent to say that F belongs to P. When P intersection S is empty, then F belongs to P, and therefore this P belongs to spec A and F doesn't belong to P. This is in one-to-one correspondence with spec AF. And what is V of F? It is P. I mean, we don't actually need this, such that F in P, and this D of F is this complement of V of F. I mean, we actually first defined V of F, and using V of F, we defined D of F, and it gives me this A such that F doesn't belongs to P. Okay, and so therefore this DF are in one-to-one correspondence with, so here this condition F doesn't belong to P is in spec of AF. Okay, so in our case, my A is this KT, and so V of T, so this is spec of A minus V of F. Okay, I mean just the DF which we are doing here. So this DF, which is also spec A minus V of F. Okay, so this VT is my singleton T, right? This maximal ideal. What is V of T? It is collection of all those P in spec A such that T belongs to P. So it is the only maximal ideal. The ideal generated by T is only maximal ideal which contains. So therefore this AT becomes, this AT is K T comma T square, sorry, T comma T inverse in our case, and then spec of this KT T here is my spec of KT minus, again let me write this here, DF, which is V of spec of T of T, which is spec of K of T minus T of T, which is spec of KT minus V of T, which is spec of KT minus, this is just this ideal generated by maximal ideal T. Okay, so this happens when we take localization with respect to some variable, sorry, not variable, some element. Is this okay? Any doubts here? So that's what we got, this spec of KT T inverse is spec of KT minus this T. This was, I think, one of the exercise left in one of the lectures. So I hope this is clear how the definition and everything works. Is this okay? If you have any doubt, please ask. Okay, clear. So, I mean, we are already above 5. So any doubt, if you have, please ask me. Otherwise, we can end the session here. I mean, this was, I mean, some, this was done to just get an overview of whatever we did in the course so far. We dealt with varieties of set, then we worked with the zero set of a polynomial, how the maximal ideals and everything. Then we did this, all the regular resolution, regular sequence, and obtaining. This question actually contained many things, calculating initial ideal Gröbner basis. Then we also went through Bookberger criteria to check whether initial term of S polynomial belong to the ideal generated by initial term of the given generating set. And then resolution, calculating Betti numbers. And then the first one was mostly the result which we used multiple times in the lecture. This result, in fact, and in fact we proved the general statement than what we used. Okay, so this please keep in mind when you are writing the exams and so on. So if you are giving the exams, all the best, and please raise your doubts in discussion forum if you have any. And thank you very much.